So today we're going to look at the crossover distortion on a PWM amplifier. I'm going to use the Bantam here, and this is a small drive that's used to replace a lot of the older, like 4000 series or 400 series in current mode, or even a 503 with Halls doing trapezoidal commutation. It's much smaller. And it's got a goodly amount of current. But just to go through the setup here, I've got a function generator outputting a sine wave, I guess 160 hertz, and I can adjust the offset to command 0. And so you can see the command to the drive is just plus or minus sine wave voltage around 0. So your command can be offset to 0. And then coming out of the drive, we deliver current to the motor. Current is just torque and will normally cause acceleration, but you need a little bit of current to overcome static friction or dynamic friction. So there's a little bit of ability to control near 0. So the crossover distortion, you don't see it in the command, but you see it in the output. As you go through 0, you get a little bit of distortion on that. So we'll talk some more about that. But the reason I'm doing this test is to help show the benefit of the Bantam versus some of the older drives. I can adjust the offset, and I can get creep one way or creep the other. So this is current, a small amount of current applied to the motor. If you have too much offset, the motor starts to spin, and eventually it just runs away. Okay, so runaway in a current mode is not good, so you got to stay away from runaway. And then, of course, you can get runaway in the other direction. But the idea of the crossover distortion is through 0, you're going to have a little bit of deadband in there. So when you optimally set it, it's not going to spin because of the inherent deadband. It's a form of hysteresis. So the hysteresis around 0 actually is beneficial for testing something in an open loop current mode. But of course, this is typically used in a system that measures position elsewhere and does some closed loop in some other controller. So a controller that closes the loop in just a dumb current mode drive. So the idea of hysteresis typically comes from an amplifier turning on an output, and you can see here a classic, push-pull or B-class amplifier. We use FETs in our drive. Sometimes you get big capacitance in the gates, and there's some crossover distortion due to that. But in this case, with these FETs, there's very low capacitance, so it's just the inherent switching of the IGBTs or the FETs that gives you a little crossover distortion. And as you can see, as you go through 0, you got to keep going before it switches over. And so there's this little bit of deadband in between. And the other concept is hysteresis. So the idea that you can start somewhere and get something, you don't, until you get through the deadband, you don't get any current. So once you pass that, then you get current. And so you need a certain amount of going over before you get any. And that goes in both directions. So let's take a quick peek at the Bantam that I'm using today and doing the comparison with an older legacy type of Copley drive from like the 1990s or maybe even late 80s. So there's two Bantams, 48 volts typical, 10 amps continuous 20 peak, and there's a 90 volt where it runs on 48 or 75, 5 amps continuous 10 peak. And the Bantam module is plugged into a development board, and of course we have reference designs, so we can share those, and you can make your own with whatever connectors you want on it. 33 kilohertz switching frequency, so kind of like the old style analog amplifiers with PWM output stages. And my current monitor is 3 volts at peak current, and we can measure the peak current. Oh, I've got enables, the limit switches. I can have a compensation for high or low inductance. I've got it set for high inductance. It's a low inductance motor, but I added some inductors at the output stage just to bring it up to a normal range. So I have the high gain setting on right now because I think I'm sufficiently above the 200 microhenry. I mean, you could go down to 100 microhenries. That should be fine. Just you might want to use the low inductance. And that does affect the crossover distortion. So higher gains decreases the crossover distortion. Anyways, the analog input is the voltage, and then there's the balance pot. There's an output for fault. I have a brush motor, so I'm hooking it up to the U and V, but if you had a 3-phase motor, UVW, so this is U and that's V for the brush motor. There's a bunch of resistors you use to program. That's right, you don't use software with this drive. You program it with resistors. So you can set a peak current by hooking up a resistor to ground at an input. You can set the continuous current to protect the motor, resistor to ground. There's a table for it. There's some formulas. There's also I squared T limiting time. So how long do you want to be at that peaking? Some of these little tiny motors might not be able to handle all 20 amps for a full second. You might want to cut that down to 200 to 500. And there's a PWM limit in the case of a runaway condition. The Bantam module plugs into the development board, and we show a typical wiring diagram. I'm using a 24 volt supply. I got the switches turned on to enable the drive. There's some heating effect. It doesn't get very hot, even if you're doing 7 amps. This is 5 watts. Good grief, that's like a nightlight. So no heat sink. I mean, there is a heat sink option, but I'm trying to think of when you might need it. I guess a really hot environment. Defense type, there's an R30, so yeah, maybe you're sitting on the tarmac and it's already 70 degrees C. But the resistors for programming the drive go here. There's a bunch of jumpers and some lights and some local bypass or DC bulk capacitance. I hooked up my motor, U and V here, and HV and ground here. I'm using this signal connector to put my reference in and my current monitors. And I'll take a quick peek at that. Yeah, so if you had Halls, you can power them and put the Halls in here. You don't have Halls for a DC brush motor. So the brush motor is just going to use, an H bridge instead of an H bridge and a half. Anyways, I put my reference in with respect to ground. Good cabling shielding is important. Enable inputs. You can see the forward path current to see what you're commanding, and then you can see the actual current monitor, 3 amps per volt. 10 amp drive is 3 volts, 10 amps per 3 volts. There's the gain select for wicked low inductance, although I didn't pull that low. Makes for better crossover distortion. And there's a bunch of jumpers and lights, and here's the potentiometer is not on the drive, right? That's, if you even need to adjust it, that's something you put on your own board. It may be that your controller has an offset balance for zero current, so it may not be necessary on the board. And that's basically it. 2 models of drives, development kit, connector kit, and a bunch of bits and pieces in the connector kit. So we're going to take a look at a comparison of an older drive, a 4212. I've got this running on the scope here, and I see about 20 millivolts of crossover distortion, and that translates into 12 amps per 6 volts current monitor on the 4212, 2 amps per volt, so about 40 milliamps of crossover distortion. It looks pretty big, and there's a big hysteresis deadband there, and it may make it difficult for tweaking the balance if there's not enough range on it. And in this case, I've tested it with a motor too, and it works fine, but I did this test just with a pure inductor, so I could get some really nice signals here for the scope. But let's take a look at the Bantam. So the new Bantam, low crossover distortion. So again, this has a different scaling. So I changed the 10 millivolts per graticule here. So I measure about 2 millivolts of crossover distortion, and given the Bantam's 10 amps per 3 volts, that's about 6 milliamps. So in my book, this looks 10 times better. I'm rounding up a little bit, but it's just a nice thing to say. So the old 4212, the 503 is a similar size. Bantam's much smaller. Again, function generators, just command and a little sine wave in, and I'm measuring the actual current monitor coming out onto channel 1. In this case, I have 2 inductors, 2 150 microhenry inductors in series with a low inductance motor, just to get the inductance up. And I use the high gain setting. I don't pull the gain scaler low. That'll add a little more crossover distortion, so I want to minimize crossover distortion here. And I'm just pounding from 24, but you could use 48, or on the on the 10 amp peak 5 continuous, you could use a 75 volt supply. I think this is the balance pot here to adjust the zero, given a zero at the input. Local bulk capacitors, probably 470 microfarads for every 5 amps you deliver. So this is a little excessive, but this board is for the 1020 also. So it's not a bad idea. Also could take 75 volts, so one development board. A couple of switches for enable. The program header is here if you want to protect the motor from excessive current. And if you had a trapezoidal Hall effect motor, you could hook up the Hall sensors here. We'll send 5 volts out from the rectified 5 volt regulator, and the motor output normally UVW, but again I'm just hooking up a DC brush motor to UNV. I would have to say that some of the old brush motors have tachometers, so this is not a tachometer drive. You'd have to use one of the plus drives if you had a tachometer, analog input to close and tune the loops, and that would require software. But typically these are used in applications where you just need a dumb drive, good quality, nice H-bridge, volts and amps, and then some outer controller measures position and sends a command for current. A little bit old school, but we still see this type of control system being used in Bantams. Gets hot, very simple, very reliable, not a lot going on, and small space. So consider the Bantam. Thanks for watching.